The concept of the magnetic monopole occupies a unique place in the history of science, straddling the boundary between theoretical physics and experimental pursuit. In its simplest form, a magnetic monopole is a particle or object that possesses a net magnetic charge, meaning it would act like an isolated north pole or an isolated south pole. In contrast to every magnet observed in nature, which always has both a north and a south pole regardless of how finely it is divided, a magnetic monopole would be a singular source or sink of magnetic field lines. Though never observed in nature, the idea of such an entity has persisted through generations of scientific thought, fueled by the elegance it brings to the mathematical frameworks that describe the physical world. Magnetism as commonly understood arises from the movement of electric charges and the alignment of microscopic magnetic moments in materials. Ordinary bar magnets owe their properties to the spin of electrons and the arrangement of atoms in ferromagnetic substances. When a magnet is cut in half, the result is not a separation of poles but the creation of two smaller magnets, each with its own north and south pole. This fundamental symmetry has led to a widely accepted belief that magnetic dipoles are inseparable. Yet the theoretical possibility of breaking this symmetry and finding a genuine monopole remains one of the most enticing quests in modern physics. The origin of the idea stretches back to the early 19th century, when scientists began developing the field theories of electromagnetism. The Scottish physicist James Clerk Maxwell formulated a set of equations that described the behavior of electric and magnetic fields. These equations contain a notable asymmetry. While electric charges exist in positive and negative forms, there is no corresponding magnetic charge in his model. Magnetic fields always arise from currents or dipoles, never from isolated monopoles. Maxwell himself acknowledged this imbalance and speculated whether a magnetic charge might someday be discovered. However, the idea remained dormant until the early 20th century. It was in the early 1930s that the concept of the magnetic monopole received a profound theoretical foundation through the work of British physicist Paul Dirac. He showed that if a magnetic monopole existed anywhere in the universe, it would explain the otherwise mysterious phenomenon of charge quantization. In simple terms, all observed electric charges are exact multiples of a fundamental unit, such as the charge of an electron. Dirac demonstrated that the existence of even a single magnetic monopole would require this quantization as a natural consequence of quantum mechanics. This insight not only restored symmetry to Maxwell's equations but elevated the search for monopoles from a speculative notion to a matter of deep physical significance. Despite the elegance of Dirac's theory, the decades that followed yielded no direct evidence of magnetic monopoles. Experimental physicists searched high and low, from the depths of particle accelerators to the analysis of moon rocks and meteorites. Some detectors were constructed specifically to spot the characteristic magnetic signatures that a monopole would produce as it passed through matter. Though a few anomalies were reported, none proved conclusive, and the existence of magnetic monopoles remained unconfirmed. In the meantime, theoretical developments continued to lend support to the possibility of monopoles. In the latter half of the 20th century, efforts to unify the fundamental forces of nature, particularly the electromagnetic, weak nuclear, and strong nuclear interactions, led to a family of models known as grand unified theories. These models predict that at extremely high energies, such as those present in the first instance after the Big Bang, the distinct forces merge into a single interaction. Crucially, these theories also imply the spontaneous formation of magnetic monopoles during symmetry-breaking phase transitions in the early universe. According to these models, magnetic monopoles would be extremely massive, far heavier than any known particle. Their density should have been significant in the early universe, yet today they appear to be absent. This inconsistency is known as the monopole problem. To resolve it, cosmologists proposed the theory of cosmic inflation. In this scenario, the universe underwent an exponential expansion within a tiny fraction of a second after its birth. This inflationary burst would have diluted the density of monopoles to a level where they would be exceedingly rare today, so rare that none may exist within the observable universe. In more recent years, interest in magnetic monopoles has resurfaced in an unexpected place: condensed matter physics. In certain crystalline materials known as spin ices, researchers have observed emergent quasiparticles that behave like magnetic monopoles. These are not fundamental particles but collective excitations of atomic spins that mimic the behavior of an isolated magnetic charge. In a spin-ice lattice, the magnetic moments of atoms arrange themselves in a frustrated geometry, where flipping one spin can result in a disturbance that propagates through the lattice as a magnetic monopole. These discoveries have provided experimental systems in which the physics of monopoles can be explored, albeit in a limited and indirect way. The study of these synthetic monopole-like objects has advanced our understanding of magnetic charge and may pave the way for new technologies. For instance, systems that use magnetic currents rather than electric ones could benefit from the ability to manipulate isolated poles, if they can be stabilized and controlled. However, these laboratory analogues do not resolve the deeper question of whether true monopoles exist as fundamental entities. One of the difficulties in detecting a magnetic monopole lies in its presumed rarity and mass. If such particles exist, they may be so massive that even the most powerful particle colliders cannot produce them. They may also interact with matter in ways that are subtle or difficult to distinguish from background noise. Some experimental strategies involve placing large volumes of detector material deep underground, shielding it from cosmic rays and radiation, in the hope that a monopole might someday pass through and leave a detectable trace. Another promising avenue is astrophysical observation. Monopoles, if they exist, may be accelerated by cosmic magnetic fields and produce unique signatures as they move through space. Efforts are underway to search for these effects using radio telescopes, neutrino observatories, and cosmic ray detectors. Yet the vastness of the cosmos and the potential scarcity of monopoles make these efforts akin to looking for a single grain of sand in an ocean. The philosophical implications of discovering a magnetic monopole are as profound as the scientific ones. Their existence would provide the missing half of the magnetic puzzle and complete the symmetry between electric and magnetic phenomena. It would validate decades of theoretical work and potentially open the door to a deeper unification of the forces of nature. It might also lead to practical applications that are difficult to predict, much as the discovery of the electron eventually gave rise to electronics, computing, and telecommunications. Moreover, the confirmation of magnetic monopoles would lend credence to the idea that the universe is governed by principles of symmetry and elegance. In modern physics, symmetry is not merely an aesthetic ideal but a guiding principle that shapes the formulation of laws and interactions. The existence of magnetic monopoles would reinforce the notion that for every electric phenomenon there exists a magnetic counterpart, even if it has remained hidden for most of human history. Some speculative theories even suggest that magnetic monopoles could play a role in cosmic evolution or the structure of spacetime itself. In certain models, monopoles are tied to topological defects in fields that span the universe. These defects could act as seeds for the formation of galaxies or influence the curvature of spacetime. Others propose that monopoles could serve as carriers of exotic forms of information or be harnessed for advanced propulsion systems, though such ideas remain far from realization. The search for magnetic monopoles thus remains one of the grand challenges of contemporary physics. It is a quest driven not only by the desire to confirm a theoretical prediction but by the deeper yearning to understand the fundamental nature of the universe. It reflects the same curiosity that led early scientists to discover electricity and magnetism, that drove Maxwell to unite them into a single theory, and that inspired Dirac to find harmony between quantum mechanics and relativity. Whether or not monopoles are eventually found, the pursuit itself has already enriched our understanding of field theory, quantum mechanics, and condensed matter systems. It has led to innovations in experimental design, inspired new generations of physicists, and expanded the frontiers of what is considered possible. If they are discovered, magnetic monopoles will become part of the known landscape of physics, reshaping textbooks and redefining the standard model. If they remain elusive, they will continue to haunt the margins of theory, a reminder of the mysteries that still await.